Good morning or good afternoon, class. Thought for days about how I was going to approach this very first attempt at a video lesson, and I really didn't come up with a great introduction. So I guess I'll just say this. I hope you and your families are all healthy. I hope you continue to be healthy, and I do hope that we get to meet again before the end of the year. But if not, we do have a plan, and that plan is to basically stay with the syllabus that we're given. There are going to be a couple adjustments that I'll send out in an update or an email. And in terms of those updates or emails, please let me know if things are coming through and if you're getting information so I can adjust if I need to. As far as these lessons, I will typically give you maybe 10 to 15 minutes tops. I will eventually post them on YouTube, and I will share a link in the Schoology course that we've hopefully created for this Calc 151. Most of you have already joined that class, but there are a few out there that I'll be getting in touch with to make sure that you can access everything that I will provide. In these lessons, they won't be quite as expansive as the lessons that I've given in the past. So it's going to be very important that, one, is you read the text the best of your ability and try the problems, and send an email or some type of a message letting me know if you're struggling with certain problems. There is a possibility that every so often I will post up maybe a solution day where I go over some of the problems that most people have. So having said all of that, let's get started. The lesson of today, and really the next couple of days, is going to be on approximation techniques. You may remember at the beginning of the chapter, I mentioned it's kind of divided into three parts. One was curve sketching with the max and the min points of inflection. Second was optimization, which were the problems that we just finished when we were still together. And the third would be the approximation techniques. The first of those is from section 4.8, and it starts with what we call the tangent line approximation. Visually, this is what the tangent line approximation is doing for us. If I'm given some function, and maybe it's a function that we really can't evaluate, it's tough to evaluate, and maybe I know it at some value, I might just say 2. So here we have some function. I know its value at 2, but when I move away from 2, I don't know the value. It's a complicated expression. So what we do is we anchor a tangent at that point. So if I anchor a tangent right here, we can see that the value of the function and the value of the purple tangent line are about the same, at least in some little window. So in other words, if I want to figure out the value of the function at, let's say, 2.2, I could really just evaluate the line at 2.2. Now there will be a little bit of a difference. Maybe at 2.2, the line would be here, and then at 2.2, the function would be here. So there would be a little bit of a discrepancy, an error you might call. So that's basically the tangent line approximation. We are going to use a tangent line to approximate the value of a function. So what it really comes down to is to draw a tangent line at a point and figure out what you might get. A quick example of that would be this problem. Let's say we want to use a tangent line approximation to approximate the sine of 0.14. Just a number I picked up. You don't know what the sine of 0.14 is. I don't know what the sine of 0.14 is. Calculator does, but let's have a historic appreciation of what this calculus can do for us. What I'm going to do is I'm going to put a tangent to the sine function to a point close to that, a very known point. For example, I might anchor it at 0. So when x equals 0, the y also equals 0. So I'm looking at the point 0, 0. In order to get the tangent line, the function is sine of x. So if I figure out the derivative of sine x, I know that's cosine x. And then the derivative at 0 happens to be 1, because that's the cosine of 0. So what I have is a slope, and I have a point. And from that, I can write the equation of the tangent line. So the tangent line, the tangent, would have the equation y minus the y value, which should just be y, equals the slope, which is 1, times x minus the x value, which is just 0. So we could just say the tangent is y equals x. So in other words, the sine of 0.14 is approximately equal to 0.14. Because I just put a 0.14 in where this x was. The reason this is helpful is it's easy to evaluate a linear function, and all tangent lines are linear functions. So I just put this number into the tangent function, and I get an approximation. If you would grab your calculator right now and find the sine of 0.14 in radians, you would find it is pretty close to 0.14. Now visually what that looks like is this. Here's what the sine function might be. And then if I anchor the tangent at 0, I get this line. With a slope of 1. And all we've done is we've figured out that the tangent with a sine of 0.14 is going to be very close to the value of the function at 0.14. That's tangent line approximation. So in your problem set, you're going to have several problems where you need to find the tangent line at a certain point and then put some other numbers in. Now, realizing that the farther away you are from 2, the less likely it's a good approximation. But that's something that you'll get into in another calculus course if you end up taking it. This does also lay the foundation for some other things that we do in calculus. But many of you won't see a course like that, but some may. So tangent line approximation. Another thing that we happen to do in this problem set is to find a differential. A differential is basically the dy of a dy dx. That's really what it is. Example. Let's say we wanted to find the differential of this function. Y equals 3x squared minus sine squared x. Well, the differential, we'll start by just finding the derivative, which we know is 6x squared. Here we're going to need a chain rule. 2 sine of x times the derivative, which is cosine of x. And so the differential is 6x squared minus 2 sine x cosine x dx. Now, what does that mean? Well, some days it's going to mean more than it does today. But visually, what this really comes down to is the following, is that this difference between the actual value of the function and the approximate value using the tangent line can be thought of as dy, or in some cases it can be thought of as delta y, sorry. They're similar, there's a minor little difference between the two, very subtle. So what we've done is if I want to find how much y changes, I can just find the derivative and multiply it by how much x changes. And that gives me another approximation technique. The final piece of today's topic would be to use an approximation technique, and I'm going to just use an example. If I want to approximate the square root of 16.5, well, we have a formula that comes from our limit definition. You might remember that f prime of x is a limit, I'm not going to write that, of f of x plus delta x minus f of x all over delta x. Well, if I restructure this, what I end up with is a formula for f of x plus delta x. If I solve for f of x plus delta x, I'm going to add f of x to both sides, and I'm going to end up with plus f prime times delta x. So I'd have to multiply by delta x first. So this is a formula that some people consider to be kind of a differential. But instead of a derivative, it's the sum of a known value x and a difference. Here's how that all could work. Given this problem, I would let x equal a known value. 16 would be a very nice value when we're talking square root. Delta x then is 0.5. And then the f of x, the function, is radical x. So when all of this is said and done, we can basically say that the f of 16 plus 0.5 equals the f of 16 plus the f prime of 16 times delta x, which happens to be, again, 0.5. Well, we know f prime is going to be 1 over 2 radical x. So I end up with the f of 16, which is 4. The f prime of 16, if I put a 4 in for this x, is 1/8. And then that, of course, is 1/2. So we end up with 4 and 1/16. So again, an historic appreciation. Think years ago how you would figure out the square root of 16.5. This is a nice approximation. It's not exact, but it's very, very close. And if you check it on your calculator, you'll see how close. That's basically a quick lesson on 4.8 topics. Tangent line approximation. What a differential is, it's just the dy of the dy dx. And then there may be a problem or two asking you to approximate a value. You just have to choose the function, a number that's very convenient when dealing with that function, and then the difference. And realizing that these are all approximation techniques. You might wonder, how does a calculator know what the sign of 0.154 would be? Or how does a calculator know the square root of 16.5? Many of those programmers need to know some of these numeric approximation techniques, and there are better ones, in order to get those values. So that's the lesson for today. Enjoy your day, and good luck, and let me know if you have any problems or questions. Thank you.